Here are a few examples of writing English sentences using predicate logic notation. These are from the end of the slides from section 1.4, which we didn't get to in class. It's also covered starting with example 5 and ending with practice problem 4 in section 1.4 of your textbook if you want to see more examples. So when we're writing English statements into predicate logic notation, the first thing we have to do is decide what our predicate should be. And so you may have slightly different answers than me depending on what you decide to name. But I'll try to continue to name, give predicate names to the most basic things that I see in the sentence. So for example, in the first one here, a predicate P of n could be the sentence 2 times n equals 5. And so that's a predicate. It really is a sentence. If you put a number like 7 in for n, it would say 2 times 7 is equal to 5, which would be false. And so given a number for n, you could decide whether this is true or false. So if that's our symbol for a predicate, then this sentence is for every, so that's upside down a for all, for every n in the domain. The domain here are the set of integers, which you could just write d and tell me that that means integers, or you could use the math symbol for the set of integers, which is this sort of bold z. I'm saying for every n in the set of integers, 2n is not equal to 5. So p of n is 2n is equal to 5, so I would want to write not pn. So this would be the quantified expression that expresses that idea. Second one says there exists a right triangle that has a perimeter 12. So I don't have a math name for the domain of right triangles, so I'll have to just make that up. So let's let D be the set of all right triangles in the world. And then my predicate here should be P of t. So my t is from the domain. It's a variable standing for something from the set of right triangles. So if t stands for a triangle, then it makes sense to have P of t stand for t has perimeter 12. So I can define the predicate, and again, you can give it whatever name you want. I'm just using P for all of these for predicate. You can give them a name that's more suggestive of what they mean. But P of t stands for t has perimeter 12. So the sentence, there is a right triangle that has perimeter 12, would be there exists something in D, right? Being in D means that you're a right triangle, such that P of t is true. T has perimeter 12 is a true statement. So that's how we would write that sentence. This last one, I'll put that on a final slide in a second. I didn't give myself enough room on here. So let's go to the next problem with these. Oh, I guess it does say we should decide which of these is true. Well, I think both of these are actually true. It's not hard to see that that it's impossible to make 2n equal to 5 if the n's you choose have to be whole numbers, have to be integers. So it is true that no matter what integer you use, 2n is not going to be equal to 5. And you may not remember your right triangles, but there is a right triangle with perimeter 12. It's sort of the basic one that everybody uses to death in a geometry course. A 3, 4, 5 right triangle has perimeter 12. So that statement is also true. So both of these statements are true. Again, we'll talk about the third one in a second. So on this next slide, we're trying to express the negation of each of these sentences. And so we can sort of parse this out in English, but I wanted to show you how the negation rule for quantifiers can be used for each one of these. So remember, the original statement here was written for every n and z, not pn. So the negation of that, one way to write it would just be to slap a not in front of it. that's literally what we mean by the negation, is just say it's not the case that, and then say the sentence again. So that's not a very useful way of expressing the negation, but that is a way of saying the negation. Just say it is not the case that for every integer n, 2n is not equal to 5, and that does state the contrary position. Our rule for negations with quantifiers, though, is that this negation can push inside these parentheses. It can push past this quantifier, so this negation can go and hit this negation, and those will cancel each other out. It's a double negation, not. But the price you pay is that the for all has to change into an exists. So the equivalent way of saying this is there is an n such that p of n. And in English, I didn't give myself enough room on here, but in English that would be there is an integer n such that 2n is equal to 5. And that's the conclusion we should have come up with anyway if we had just started from this and not done symbolic logic. If I say that every integer n doesn't satisfy p, which is what I'm saying here, the contrary position for that would be there is an integer n that does satisfy p. So the negation of everything doesn't is something does. So here we have everything doesn't satisfy p, and here we have something does satisfy p. So those are the two contrary positions if you were having an argument about this. The next one, again, remember the original was there is a t in D, and we defined those in the last slide, P of t. And so that's saying, in the abstract, it's saying there is something that satisfies property t. So the negation ought to say that everything in t doesn't satisfy p. And again, we can think of that as a formal rule with our quantifiers. To form the negation of a sentence, I'm just sticking a not outside of it. So this is my original sentence, and I'm putting not on it. That negates the sentence, but my rule for negations and quantifiers say that I can push that negation symbol inside past the quantifier, so that negation moves to here. But the penalty is that the quantifier switches to the other one. So instead of there exists t and d, it's for all t and d. So this is the equivalent of my negated sentences. So these two things are negated. Again, in the abstract, if we think of this original sentence, it says there is something that has property p, and the negation then says everything doesn't have property p. So the negation of something does is everything doesn't. So let's continue with the last example that was at the bottom of the slides. I didn't have room to write on that slide, but if you want to look back at it, it says there is a natural number n for which n is prime and n plus 1 is a perfect square. So let me write P of n is the predicate, n is prime. Let's use S to mean n plus 1 is a perfect square. And so the sentence that we're trying to represent is there is a natural number that it does both of those things. So we would write that there exists a natural number, and natural numbers for us would be our bold-faced n. It's one of the piece of notation. Again, you could just write the generic letter D there for domain and then say the domain D is the set of natural numbers. But the natural numbers are the numbers 0, 1, 2, 3, and so on, the non-negative integers. So I need to say that there is an n so that P of n is true and S of n is true. So that'll be my original statement. The negation of that will just be, one way of doing it is just slap a negation sign outside the whole thing. But again, we want to be able to rewrite that so we don't have that negation sign outside. So if I push this negation sign inside, the not would go into here, but the penalty is that the quantifier will flip over. Now, one thing that's important is that that negation sign just goes inside. It doesn't just happen to go hit the first thing among all of the things inside. So if what's inside here is a compound sentence, then the negation is going to apply to the whole compound sentence. So I'm going to have to add parentheses to denote that. Now, that raises something that we looked at before, which is De Morgan's laws, which tells us how this negation sign can push inside of parentheses. We know that the negation can go inside of parentheses, and the consequence is that this connective changes. The and will change to an or. So I could even go one step further here and write this as for all n and n not pn or not sn. And so back in English, so this will be the negation, and that's about as much as I can simplify it. These two statements are negations of each other. They're not equivalent. They're exactly the contrary point of view. So remember the first sentence, the original one said, there is a number that's prime and that's where n is prime and n plus 1 is a perfect square. And here it'll say for every number either n is not prime or n plus 1 is not a perfect square. And that's kind of a mouthful, but that's about as simple a way to state the negation as you can.